Since there are two types of acceleration for the pendulum, we have to look at each one individually. So we're going to start with the centripetal acceleration first, which is a radius that we see right here. This, of course, follows the exact same rules and properties that we learned before about centripetal acceleration and circular motion. Now, just a quick review of centripetal acceleration. We know that centripetal acceleration always points towards the center of the circle. It does not change the actual speed of the object, but rather the direction of its motion. Centripetal acceleration is equal to the tangential speed of the object squared divided by the radius of the path that it is taking. It is also equal to the angular speed squared times the radius as well. However, most times when we're dealing with a pendulum, we'll be dealing with tangential speed, but not always. So it's always important to know that we have this one in the background dealing with angular speed instead of tangential speed. Remember that accelerations are in fact vectors, and they have a direction that is always going to point towards the center of the circle. So as far as the radius is concerned, the direction of the acceleration never changes. But from our outside perspective, we actually see the direction change. So either going to the left, going up, going to the right, or at some odd angle. However, as far as the radius is concerned, the acceleration is always pointing inwards. Again, since the acceleration depends on the speed squared, it will be greatest at the bottom of the swing where I have the most amount of speed. However, on the amplitudes, the pendulum stops moving. And since it stops moving, the velocity or speed then is zero. And so I have no acceleration at the two ends of the motion. Again, at the bottom, I have maximum speed. So I'd have maximum acceleration. Because through all parts here, the length of the string remains the same. So for the pendulum's motion, I have a constant radius, only the speed changes. And that is what is going to determine the strength then of the centripetal acceleration as this thing moves. The tension force in the wire can be found then through our problem-solving process. Step one, always a free body diagram. And so we can see gravity pulling down and the tension force pulling along the wire. However, gravity is not parallel nor perpendicular to the motion, and so we're going to have to break gravity up into its component. This here is very similar to a block on an incline, where the normal force is in the same direction as the tension force. The angle between gravity and my axis with the normal force is equal to the angle at the base of the incline. The same thing is also true here, where the angle between the axis along the tension force and gravity is the angle that the wire is at with the y-axis. So the angle here and here are in fact the same. So I can now break gravity up into its components, and very similar to the incline, I see that the part that's parallel to the motion is equal to Fg sine theta, and the part perpendicular to the motion is Fg cosine theta. Again, very similar to what we see with a block on an incline. I'm not going to worry about the Fg sine theta right now because that is along a different axis of interest. I want to focus on the tension force. So I do have to look at Fg cosine theta. And since net force must equal ma, I can say that the tension force plus the vector value of this Fg cosine theta must equal mac. Now, if you remember, when we're dealing with centripetal motion, since there's nothing about centripetal acceleration that can be negative, because any value squared is a positive, and radius is always a positive, AC must always be a positive value, which means this must always be a positive value. I cannot control that. This means any force that points into the circle Anything that goes towards the same direction as the tension has got to be a positive. And anything that's pulling out of the circle, such as Fg cosine theta, must be a negative. So I'm going to just say F tension plus negative Fg cosine theta must equal MAC. AC is, of course, V squared over R. And if I look at this, the only thing that I do not know would be my tension force. So I can easily manipulate this equation to solve for my tension force. And this is true now for any part of the swing. All I have to do is change the angle for whatever location this is in. Please note that if I'm at the bottom of the swing, I would have an angle of 0. So this would be an angle of 0. The cosine of 0 is 1. So then I would just have tension fighting gravity equaling my net force. Here I can see the three classic cases or positions that a pendulum will be in when we're looking to find the tension force. We have at the very bottom where theta is 0, so I can just go Ft equals force gravity plus m times the centripetal acceleration. We have some other angle between my maximum angle where I'm at rest and 0 degrees. So I'm just going to have cosine theta right here. And I really do have cosine theta in this case as well again. Just remember, since my angle is 0, the cosine of 0 is 1. So it's kind of hidden in plain sight because we don't write the 1 because it's just implied. If I'm at the very top or at amplitudes, then my velocity is 0. If that's the case, then again, my acceleration is 0, which means my net force is 0, and my tension force and my Fg cosine theta need to balance out. Now, it's very important to stress again that the acceleration is 0 only along the radius axis. It is not truly 0 on the bob itself, because I do have a tangential acceleration still in play. Pendulums are never in equilibrium. And again, when I'm at the bottom, I see I have no tangential acceleration, but I do have a centripetal acceleration.